Hi, my name is Matt. I'm doing a tutorial today on a directional Kuwahara filter. This is all based on my previous video on building a non-directional Kuwahara filter. We're going to use the code from that video as a starting point. So if you haven't followed along with that, I will link it again in the description below. Um, the difference between the directional Kuwahara filter and the previous Kuwahara filter is I think it looks considerably nicer. This is the old one. This is the new one. As you can see, the directional Kuwahara filter maintains edges a lot better. It preserves detail. So yeah, overall, it's a better looking filter in my opinion. It is, of course, slightly more expensive to compute. Um, to get there, we're going to start from the results of the previous video. We're first going to make them anisotropic. This will give you a separate control over the radius of the x and the y axis. You can stretch it in one direction to get slightly different results. After that, I'm going to show you how to calculate the relative luminance of the image. This is a slightly fancier black and white filter. We're going to use the relative luminance to calculate a Sobel operator, which is an edge detection algorithm. Here you can see the exact same effect, but splits into the x and the y gradients. Because we're calculating an x and a y gradient, we can use that to calculate an angle. This shows you the angle per pixel. Probably won't say a whole lot apart from we're going to use this to then rotate our Kuwahara samples. As you can probably tell in the video, there is a bit of noise happening. That is because the values from the Sobel operator are very close to zero, and it can't calculate a nice angle from that. This didn't cause any issues for me because this is, well, happening on very flat surfaces. But if this does end up causing issues for you, you might have to see if you can clamp the angles if your gradient becomes too small. But we'll have a look at where you would do that later. So yeah, with that said, let's get started by well, starting from the previous code and making it anisotropic. So to make the material anisotropic, we're starting from the same base. The settings that you're currently seeing here are still almost identical to the previous video, but we want to split this radius parameter into a separate x and a y. So what we'll start with is we'll add an append node, rename this to radius x, create a radius y, append these two together, round that, and plug that in. This won't automatically work because the code is currently expecting a float, not a float 2. So if I open up the code, we see a few mentions of radius. All of these now either need to be radius.x or radius.y because the radius parameter is coming in as a float2 now. So the way I'm deciding whether this should be .x or .y is just where they're sitting in these little float2 constructions. If they're in the x element, it's .x. If they're in the y element, it's .y. Same here. I'm using the j as the x element, and I'm using k as the y element. So I'm just treating these as x and y. The biggest difference is this float, that is this power, because instead of doing a power, we're now going to do radius.x plus 1 times radius.y plus 1. The reason we're doing this is the n value was previously just finding out how many samples we were doing in a square. but our value is no longer a square because it's anisotropic. So we are instead calculating potentially a rectangle. So we have to split it this way to get the same result. If I now copy this code, paste it into the shader, let that compile, we should have an anisotropic filter. I let it finish compiling in the background, and we now have the separate X and Y sliders. You can now stretch the effect. You now have a very, very thin filter on the X-axis and a longer filter on the Y-axis. This works great if this is the effect you're going for, but I would like to rotate these samples based on the brightness of these pixels. So let's have a look into how we start doing that next. The way we're going to calculate the brightness of the pixel is by using the relative luminance. The relative luminance is the perceptual brightness of a pixel or of a color, because we interpret the brightness of red, green, and blue channels differently. How we're going to calculate it is we're going to use this formula. We're going to take the input red channel and multiply it by 0.2126. We're going to take the input green channel and multiply it by 0.7152. And we're going to take the input blue channel and multiply it by 0.0722, which seems straightforward enough. So I'm just going to add a multiply node and then use the values. What was it? 0.2126, 0.7152, and 0.0722. We've now multiplied these values together. The next step was summing them. So I'm going to split this this vector, break it into 3 float components, which I'm then going to add together. And if we look at that, we get a black and white filter. This is a, well, bit of a gross way of doing it. I'm not a big fan of it. But there's another operator that does the same thing as this, which is the dot product. What the dot product does is it takes the elements of one vector, multiplies them by the elements of another vector, and sums them together. So in our case, we're going to get the input red channel times the, 0.2126. Then we're going to get the input green channel and multiply it with 0.7152 or something like that. You get the drift. So the difference here is we're going to replace all of this with just a dot product. To get the exact same result. We will be writing this in code in a bit. I just wanted to make sure that the concept was clear. We will now use the relative luminance to calculate a Sobel operator, which is an edge detection filter. The way it works is for every pixel, we're going to sample the 8 neighboring pixels and multiply by specific values. When we sum these values, we can calculate a gradient for where the values are higher and where the values are lower, which we can then later use to calculate the gradient's direction. So we're going to do this in a separate custom node first, and afterwards we're going to be building it into the Kuwahara filter. So what do we actually need to build the Sobel filter? Well, we're going to start with a gradient x and a gradient y. These are just going to be the values that we're going to store our gradients in, obviously. and we're going to need all the Sobel multiply operations. These are just coming straight from the Wikipedia page. For the x-axis, we're doing -1, -2, -1, 0, 0, 0, 1, 2, 1. And for the y, we are using -1, 0, 1, -2, 0, 2, -1, 0, 1. Again, both of these are straight from the Wikipedia page. And we're also going to need an index. And why will become clear in a second. We're going to be looping through both the x and the y axis just to find the surrounding pixels. So I'm going to start at -1. Equal 1, x++. And we're going to do the exact same thing for the y-axis. And using these two, we're going to calculate an offset. Right now, our offset is going to be between -1 and 1 on both axes, but well, that's not ideal because our screen UVs are going to be between 0 and 1. So we're going to want to calculate the size of a pixel to multiply this by, so we can do our offsets by a single pixel instead of a single screen size. To do that, I'm just going to calculate a texelSize, which is 1.0 divided by our view size, the view size being this input parameter that we're going to add to the Sobel operator custom node as well. So we're just going to multiply this by the texelSize. What we'll then want to do is just sample the post-process input texture with the offset that we've currently calculated. So let's store that color in a using a scene texture lookup of UV, which we're gonna again just use as a as an input plus offset. We want to sample scene texture 14. That's the post-process input 0. Set this to false, and then we only care about the X, Y, and Z components. We want to, well, calculate the relative luminance from this, which I just showed you how to do using the dot product. So we want to calculate a pixel luminance. That's going to be pixel color. Oh, it's dot pixel color. And then the other value we want to plug in is, let me just open that on my second screen, like this. So we now know the relative luminance of every single pixel surrounding the pixel we're currently sampling. And we want to just increment our index at the end of every one of these, which will help us do these do the lookups into the Sobel arrays. So for the gradient x, we want to add the pixel luminance times Sobel x index. So we're just cycling through this array and multiplying the luminance of that current pixel with the Sobel value. We're going to do the same thing for the y, so pixel luminance times Sobel y index. And yeah, we're incrementing the index. Something some people might have noticed is that the fourth array element is 0 for both of these. So we're doing a texture lookup and then multiplying both of these values by 0. That's a bit of a waste of a texture lookup. So if index equals 4, we only want to increment the index and then continue. this will skip the rest of this for this one index, which will save us a texture lookup, which is a small optimization. For now, I'm just going to return the length of a float2 that is gradient x, gradient y. This is just temporary to visualize what our work so far would look like. This will just give you an edge detection filter. I'm going to copy that, and I am going to create a custom node. I'm going to paste our code into the custom node. Okay. I'm going to add some inputs. So the inputs we needed were the scene texture, same as last time. If we don't have it hooked up somewhere, it's not going to be available, even if we're not directly referencing it by name. I'm going to add the UV as an input, and I'm going to add the view size as an input. The UV and the view size are being used by name, of course. So just going to use these variables because, well, we already have them. Why not? And as you can see in the preview already, we're getting some edge detection. So that is step one of the Sobel. What we can do with it from here is calculate the angles. So to calculate an angle from this, it's actually fairly simple. We're just going to use an atan operation and divide gradient y by gradient x. Now if we return this angle instead, should have cleaned up this graph slightly better, but we're going to get rid of this and merge it all into the Kuwahara filter in a bit anyway. You're getting this angle. This is currently from negative half pi to half pi, I believe. So especially in the darker areas, these values are negative. Some of our values are, well, way above 1. But that's fine for what we're going to do next with using it as a rotational value. Before we do that, though, there's something that you might want to watch out for, which is in this division here, there is a chance that your gradient x equals 0, in which case you're dividing by 0, and that is something you tend to want to avoid. So something I'm just going to do is leave this set to 0, and then if gradient x, if absolute gradient x equals, is greater than 0.001, some small value, in that case, you'll want the angle to be equal to this. Otherwise, I'm just going to leave it to 0. This should, well, prevent some unwanted behavior. So now we'll be putting it all together. So I'm just going to split my view in Visual Studio. On the right side of the screen, I have the Sobel filter. On the left side, I have the Kuwahara filter. We're going to want to do all of this, all the variable setup, early on in the code. And then we're going to want to actually calculate the angle per pixel before we do, well, anything for the Kuwahara filter. We're now in the same custom node. We are now calculating the angle for every pixel, and we are still doing the Kuwahara filter, but they are not doing anything together yet. So we're going to want to calculate. Well, a rotation value from the angle. This is relatively simple. We're going to do this through some 2D rotation math using a sine and a cosine. The math for this can be found on this rotation matrix Wikipedia page. It's fairly straightforward what we're going to do. We're going to calculate the cosine of the angle and the sine of the angle. We're going to multiply it with the x and the y offset, and we're going to use that as our new offset. So I'm going to be calculating the sine and the cosine before our for loop because it's going to stay, the values are going to stay the same for the entire for loop. So that would be float s equals sine angle and float c equals cosine angle. Let's see, is this all still correct? Yes, I believe so. One thing I'm going to change, a bit of an optimization, is instead of dividing this by view size, I'm going to multiply it by texelSize because a divide is a slightly more expensive operation than a multiply, and this way we're only doing one divide instead of well, however many samples we're doing. To then rotate this, we are, let's see, where do we actually want to do that? I think we want to just rotate the offsets, or do we, sorry, just thinking here for a second. Let's calculate another value. It's going to call that offs, which is this. Because we want to rotate the position times the texelSize. Yes, that sounds right. So the offs equals offs.x times c minus, so this is multiplied by that cosine, just following the rotation math from the page I just showed you. And then the other component is offs.x times s plus offs.y times the cosine. So this should rotate your samples. I'm then going to copy this, go back into Unreal, clean this up a little bit, paste this in, and I'm going to let this compile. I'm going to clean this up just a little bit. I'm going to let this compile, and when this is finished, hopefully it will all work. While that compiled just fine, I noticed a mistake I made in well, earlier in this video. The view size is coming in as a float 2, not as a float, because, well, you obviously have a width and a height to your screen. So this should be a float 2 as well. I've already updated that in Unreal, where the directional Kuwahara filter is now working. The directional filter obviously does a much better job at preserving edges and details while retaining the painterly look we were getting from the previous iteration of the filter. It is considerably more expensive though, as you're doing 8 more texture samples, you're using more math, and you're using sines and cosines. If you end up using this in a project, it is worthwhile to profile it before shipping to make sure that this is not too expensive for you. I made this video because it was requested a lot in my YouTube comments. If you have other tutorials you would like me to do, please let me know and I'll see if I can do them. If you have questions about this post-process filter, let me know in the comments. And I would love to see what you end up building with it. So please let me know in the comments or send me a message on Twitter or ArtStation. Otherwise, this is the end of the video. Thank you very much for watching.